Okay. So last class we talked about mean and variance of a marginal distribution, right? So in the previous chapter we talked about mean and variance, right? Remember when we were rolling the dice? We get we have an expected value for what we get, right? But now assume that we have a two-dimensional distribution, right? So like think about, like the cell phone, number of bars that you get on cell phone and the response time, right? And let's say you want to calculate the expected value for the response time, right? Or the expected value for the number of bars on your cell phone, right? So that is basically the expected value of a marginal distribution, right? So basically we want to calculate the mean value for x, right? Or the mean value for y, right? So that means that we don't care about x, right? When we want to calculate the mean value for y, we don't care about x. We just want to calculate the average value of y, right? And similarly, when we calculate the variance of x, we want to find out how spread x is, right? Meaning that we don't care about y, right? So the first thing you have to do is when we have a joint distribution, you have to find the marginal, right? So you'll have to find f of x if you want to find e of x. And similarly, if you want to find e of y, the first thing you have to do is to find f of y, right? Okay, so let's look at an example, right? So here again, we have, this question that we have, number of bars on a cell phone. So that's one random variable. And the other random variable is the response time in seconds, right? So the entire PDF, or in this case PMF, because it's a discrete distribution, is represented by these 12 numbers, right? So these 12 numbers tell us everything we need to know about this distribution, right? All of the other numbers are actually estimated from these 12 numbers, right? So let's say we want to calculate e of x and e of y, right? So the first thing we have to do, we have to calculate the expected, the marginal distribution of x, f of x, right? So to calculate f of x, the marginal distribution for x, remember all we have to do is to add up these basically four numbers, right? So 0.001 plus 0.002 plus 0.002 plus 0.15. If we add those four numbers up, we get 0.2, right? So what does this number mean? It means that this is the probability of having one, bars on your cell phone, right? So remember, when I describe this, I don't care about the response time, right? I don't mention the response time at all. I mentioned that 0.2 is the probability of having one bar on your cell phone, right? So that's the meaning of the marginal distribution. It means that we only care about x, right? And so forth. So we calculate for x equal to 2 and for x equal to 3, right? And remember the definition of expected value was sigma x f of x, right? This was the definition of e of x, right? Or mean, right? So basically now what I have to do is that I multiply x by f of x. So basically 0.2 multiplied by 1, that for some reason my Siri got activated. So this is 1 times 0.2. This is 2 times 0.25, so that's 0.5, right? So this row here shows me x times f of x. And to calculate the mean, all I have to do is to sum up these three numbers, right? So this plus this plus this, right? And the answer is 2.35, right? So I'm done. E of x is 2.35. Right? So it's always a good idea to go back and at the original question and see what this number means. So this number means that, in average, you can expect to have somewhere between here, right? Between 2 and 3 bars on your cell phone, right? Basically in this problem. So that's the mean number of, bars on the cell phone. So any questions about E of X? Oh, okay. So now we have to calculate, the question also wants the variance, right? So we have to calculate the variance of X, right? So remember the equation for variance was, where should I write? So here probably. So variance was sigma x squared f of x minus mean to the power 2, right? So that was the equation for variance. So therefore, I have to calculate x squared f of x, right? So here in this, in the last row, I calculate x squared times f of x. So 1 squared times 0.2, so that's 0.2. And then the next one is 2 squared, which is 4, times this guy, 0.25. So 4 times 0.25 is 1. And the last one is 3 squared. That's 9 times 0.5. So that's 4.95, right? And we add up these numbers, because remember the definition of variance is sigma, right? So we add up these 3 numbers and we get 6, right? So variance is going to be 6.15 minus mean to the power 2. And the mean is 2.35. So this is the variance. Yep.
In your slides, for EY, 7.61 minus the 16.2, I think it just goes to be 6.2. Is that 16?
Oh, the next line? Yeah. So, so this line. So this is 7.6 minus 2.49 to the power 2, and 2.49 is basically the mean for y,
Yep.
right?
I just wanted
Oh, I see. Yeah, you're right. Thank you. Yes, you found another mistake. Yeah, thank you. Yeah. Yeah, so, 2.49 to the power 2 for sure is not 16, right? What is it?
it's 6.2.
Oh, okay. Thank you.
So I just added an extra one there.
Yeah, thank you. Yeah, in fact, that's a very good point, right? So imagine that, like, I did my computations, right? Because if it was 16 here, I would get a negative number, right? So 7 minus 16 is approximately minus 9, right? Is that possible to get a minus value, negative value for variance? Never, right? Variance is always, always positive, right? And in fact, the proof is very simple, right? If you like math, I encourage you to try to prove it, right? It's a very simple inequality that basically says sigma x squared f of x is always more than or equal to mean to the power 2, right? This is a simple inequality that you can always prove, right? Meaning that this term is always more than or equal to this term. When is it equal to the other term? So when is the variance 0? No, standard normal doesn't have a variance of 0. It has a variance of 1, in fact.
When all numbers are same?
Almost, yeah. So basically, like, for example, if we have a die which has number 1 on all of its sides, right? So whenever we throw the die, we get 1, right? So that has a variance of 0 because we always get 1, right? So basically, if the variance is 0, it's not a probabilistic problem anymore. It's deterministic, right? That's called deterministic, meaning that you know the outcome before the experiment, right? Okay. So yeah, you can't get a variance of 0 either, right? So the variance is only 0 when, there's only one thing possible, right? It means that, the distribution doesn't vary. So yeah, I'm not going to go through the steps for E of y, but I encourage you to go through them at home, right? It's exactly the same for E of x and variance of x. Any questions? Okay. So we can define conditional probability like before, right? Conditional probability was, difficult even for, discrete random variables that we had before. So this is even more difficult to, to get your head around. So we do try to do a couple of examples so that it makes more sense. So basically, the conditional PDF of y given x is defined as follows, right? So it's the joint distribution. So the definition is the joint distribution divided by marginal, right, of x, right? This is f of y given x. Right? So you divide the joint distribution by the marginal of x, and you get, the conditional probability. And in fact, it's quite similar to the, to the discrete case. Remember, we defined P of A given B as P of A and B divided by P of B, right? So this has, a lot of similarities to that original equation that we had before. And it satisfies these probabilities. So first of all, it's always positive, right? Probability cannot be negative. And it can be more than one. It's OK, because this is the integral of this is probability, right? So as you can see in the third property, if you want to calculate probability of y being in some set, given that x is something, that is going to be the integral of basically the conditional probability, right? And because the integral is probability, then this thing can be actually more than one. This thing can be 10, can be 100, can be any number, but it's positive. Any questions? Okay, so let's try to do an example. So remember the running example that we had, for a computer connecting to a server and the server authenticating the computer, right? So basically what we want to do for that question, we want to calculate probability of y. Sorry, not the probability, we want to calculate the PDF, right? So we want to calculate f of y given x. Right? And f was, I can actually show you guys what f was. Yeah, so this, actually we don't have the f. Yeah, so it's in the previous, but it was a two-dimensional, so it was defined here, right? It was only defined here, and it was e to the minus, I think, 0.002 y minus 0.003x or something like that, and then multiplied by some k, right? This was f of x and y. Right? So this can be incorrect. Maybe this was x and this was y, but it was an exponential function, right? That's what I mean. Okay. So the first thing we need to do to calculate the conditional probability of y given x is according to the equation here, we have to calculate the marginal probability of x, right? So actually, I don't know why I did that. It's here, right? This is f of x and y, right? So e to the minus 0.001x minus 0.002y. Okay? So this is the joint PDF. So to to calculate the marginal probability with respect to x, I have to integrate with respect to y, right? This is very important that you have to, you have to properly set the bounds here. So remember the function was defined here, right? And that means that when you integrate with respect to y, y varies from here to infinity, right? What is here? This is y equal to x to infinity, right? So y varies from x to infinity, right? The bounds are always very important. So when we want to do this integral, this is a function of x, right, this part. So a function of x is constant with respect to y, so it comes out of the integral. And here again, we use this basically equation that e of ax dx is equal to 1 over a times e of ax, right? So the integral is going to be this thing here. I think there is a minus missing here. Yeah, there is a minus missing here. So there must be a minus here. Right, Michael? Yeah? Okay. But there's no minus missing here because we have a minus here, and e to the minus infinity becomes 0. It becomes e to the minus infinity minus e to the minus 0.002x, and the minus and this other minus cancel out. So at the end, oh, another x is missing here. Right?
Yep.
So now minus 0.002x minus 0.001x, that's going to be the summation of these two. So this is actually correct. So I think the problem is that, I'm opening a PowerPoint, in Keynote. So I think that the notes are actually correct, hopefully in the PDF that I uploaded. So basically now I have, so what is this thing that I got at the end, right? This is f of x, right? Yeah, and we see that, f of x is not a function of y, right? It's just a function of x. So to calculate f of y given x, I will have to define the joint PDF by the marginal, right? And at the end, this is the equation for the conditional probability. Any questions? So see, this is 0.001x minus 0.002y divided by 0.003x. So this goes to the numerator and it becomes positive, right? So it becomes plus 3 minus 1, so it becomes 2. Yeah.
Are we going to have any handout for the integral formula?
What is it?
Are we going to have any handouts for the...
No, so basically whatever is in the crib sheet is there, right? So we haven't, used any complex integrals so far, right? Most of them are, actually we have used this one repeatedly, right? So like I said, I don't want the challenge in this course to be the integral part, right? So as far as, you are expected to know, simple integrals like this, but not, complex integrals. We will actually do one complex one here today. That's the most complex, that you will do in this course. Any questions? Okay. So now, after we have found the PDF, we want to find the probability that, y was the time that it takes for the server to authenticate you, right? So the time that the server takes to authenticate you exceeds 2,000 milliseconds, given that x is 1,500 milliseconds, right? So we want to know what's the probability that it takes more than 2 seconds to be authenticated if, the time that it took for you to connect to the server was 1.5 seconds, right? So what we do is that we have the joint PDF, so this equation, right, that we calculated at the end. So we plug into this equation x is equal to 1,500, right? So we plug in x equal to 1,500 in this equation, and I integrate this equation. So f of y given x is 1,500 dy from 2,000 to infinity, right? I wanted to calculate the probability that the time exceeds 2,000, right? So this is the probability that I want to calculate. Right? So you can see the steps here, right? So I integrate this function, d of y, from 2,000 to infinity, right? So as you can see, I plugged in 1,500 for x, and the rest is simple. It's a simple exponential integral. So yeah, here we have the negative sign here. The negative and negative cancel out. And at the end, I get e to the minus 1. Right? So let's see if we can actually plot this to see visually what this means. So again, the function is defined up here, right? So it's defined here. And I know that my x is 1,500. So it means that, I'm somewhere on this line, right? So I know for sure my x is 1,500. So I'm living basically on this line, I'm restricted to this line. I can't be here, I can't be here, right? And I want to calculate the probability that y exceeds 2,000. So if this is 2,000, I just calculated the probability that I'm here, right, on this section of the line, right? So based on what we calculated, we can say that the probability of being in this section of the line is 1 minus e to the minus 1, right? And the probability of being in this section of the line is e to the minus 1, right? So why I'm not here, right, or here? Because I conditioned the problem that x is 1,500, right? So for sure, I know that I'm somewhere on this line. Any questions? So it looks quite complex, and the equations are quite large. But again, I think these are much easier than chapter 2, right? These are not, intuitively difficult to imagine. You just have to follow a couple of steps. Okay. And, to help with your intuition, with conditional probability and Bayes theorem, you can watch this video. I think it's a cool video that shows, how these are, difficult concepts, and we often make mistake about them. How many of you actually did watch the other video that I recommended, the coincidence video from Vsauce guy? So raise your hand if you watched that one. Yeah, I think it's very interesting. If you didn't have time, it's a very cool video. I think it really opens your mind into, what in this world can be, caused by coincidence, and what is actually not coincidence, right? You hear for many, things that happen, people say, oh, it was meant to be, So many things you realize that, they can be coincident. Okay. All right. So let's do some review of, again, this question. So we have this joint PDF, right? This is our running example. And we calculated the probability that y exceeds 2,000 for this, right? So we did this in two different ways. One solution was that we said, oh, the probability that y exceeds 2,000 is the summation of this area plus this area, right? Which, wasn't the best solution. And we saw that a better solution to find out what is, the probability of y exceeding 2,000 would be to find the marginal distribution of y, right? So meaning that you integrate with respect to x from 0 to x equal to y, right? So this line is x equal to y, right? So you calculate f of x and y dx. X varies from x varies from 0 to y, right? And this is f of y, right? So it's the marginal of y. And after you find this, you integrate f of y from 2,000 to infinity, right? That's the easier solution. Any questions about how we did this? We did this on Monday. Okay. So you can see actually the steps here. First, we calculated f of y, which is this, right? And again, you can see that it's only a function of y, right? There's no x here. And then we calculated the integral of this function from 2,000 to infinity, right? And we get a number here, 5%. Right? And we just introduced the concept of the conditional probability, right? Which means that it's the joint PDF divided by the marginal, and it is quite similar to what we had before. P of A given B is P of A and B, right? Divided by P of B. And P of A and B is actually this guy, right? And we actually calculated the probability that y exceeds 2,000 given that x is 1,500, right? That's what we just did for this PDF. Right? So a very, very common wrong solution for this problem, right? So I give you this PDF, right? Let's say from an experiment or from physics or from mathematical modeling, you somehow get this equation, right? You know that your f of x and y is this equation, right? And you want to find this conditional probability that y exceeds 2,000 given that x is 1,500, right? So it's a very, very common incorrect solution to plug in, in this equation. So we have an equation for x and y, right? So you say, okay, x is 1,500. I'm going to set x to 1,500 in this equation, right? So I'm going to say, oh, you want this probability. This probability is going to be probability of y more than 2,000, given that x is 1,500, is integral of k e minus 0.001 x, and x is 1,500 times 1,500. Actually, one extra zero, so 1,500 minus 0.002y, right? dy from 2,000 to infinity, right? So basically, all I did here is that for x, I repeated the same equation, but instead of x, I plugged in 1,500, right? Because I said that, okay, the question is telling me that x is 1,500. That's not correct, right? You can't simply plug into the joint PDF x is equal to 1,500 to calculate the conditional probability, right? What you have to do is what we just did. First, you have to calculate this equation, f of y given x, and to calculate that, first, you have to calculate the marginal probability of x, right? You divide the joint PDF by the marginal, and once you have this equation, then you are free to set x equal to 1,500. you can't set x equal to 1500, you know, in the original equation. So this is basically wrong. So I will try to explain here intuitively why, you know, this is wrong. You know, why, even though we know that x is 1500, we can't simply plug in x equal to 1500 in this equation. So basically, this is what we just did, right? First, we calculated f of y given x. And for that, we had to calculate f of x, which was this guy, right? And once we have this equation, I can plug it in here, right? And I can say that, okay, instead of x, I'm going to plug in 1500. So this is the correct solution. And this is what we just did. Why is this correct? Because I used the equation for conditional probability. Any questions? Right. So for now, just accept that we have to do this. I will try to explain, you know, it's hard to explain in this equation, in this example, but, you know, in another example that's easier, you know, to understand. I will try to explain why we have to divide by this, you know, marginal. Okay. So this is the example that I try to explain why we have to divide. So, you know, the first thing I have to say here is that all of the data here is made up. These are not, you know, historic real data, right? So assume that we are looking at two types of surgery, knee surgery and brain cancer surgery, right? And X here defines my type of surgery. So X equal to 0, my random variable X equal to 0 means knee surgery. And my random variable x equal to 1 means brain cancer surgery, right? And my random variable y represents the survival time, right? So what's the chance of the patient surviving more than 3 years? I represent that with y equal to 1. And the chance of surviving less than 3 years, I represent that with y equal to 0, right? So these four numbers give me my joint PMF, right? Probability mass function. So everything that I need to know is in these four numbers. So assume that we want to calculate the probability of surviving more than 3 years, given that the surgery is a brain cancer surgery, right? So basically, if we just plug in, right? So here, this is my joint PMF. So for example, f of, so x equal to 1 and y equal to, so survivor more than 3 years, y is 1, right? Y equal to 1. So what is this f? F of x equal to 1 and y equal to 1 from this table. What is it? 0.04. Exactly, 0.04, right? So it's 4%. So it's incorrect to simply plug in, you know, if you want some probability, right? Probability of surviving more than 3 years, given that, you know, this is a brain cancer surgery, it's wrong to say, oh, okay, I know that it's a brain cancer surgery, so I'm going to plug in x equal to 1, and then I look at what, you know, represents my answer. So y equal to 1 represents my answer, so the chance is 0.04. No, that's incorrect, because this number actually means the chance of, you know, being, this is and, right? This is not given that, right? So here the question says given that. That means it's a conditional probability, right? So if I actually like draw circles that represent different masses here, the biggest circle goes to this guy, right? 90% chance, right? So it's this circle here, meaning that, knee surgeries are much more common, right? 91% of the surgeries are knee surgeries and 9% are brain surgeries, right? So basically the biggest mass corresponds to this guy here, 90%, right? So in order to find the correct conditional probability, we knew this from chapter 2 or chapter 3? Chapter 2, I think. So what we did in chapter 2 is when we wanted to calculate the conditional probabilities, we always divided by the marginal, right? So this is my marginal probability, right? So these two numbers, this is f of x, and these two numbers, these are my f of y, right? So given that it's a brain cancer surgery, I will have to divide by f of x. So f of x here is 0.09, so 0.09, and this is 0.4, so the answer is 0.44, right? So I don't know how well I explained with this example. Hopefully it's more clear now. But basically the idea is that whenever you want to calculate a conditional probability, right? Given that, you do have to use the equation for the conditional probability, meaning that you have to say this is f of x and y, and you have to normalize it by f of x, right? Marginal distribution of x. Right? And looking back at the numbers, it makes sense, right? So if our answer was, it's 4%, when we look at these numbers, right, 4% is a very low chance that somebody survives a brain cancer surgery after more than 3 years, right? We see that when we actually normalize by the probability of, by the marginal probability of x, we get much higher chances, right? We get like 44%. There's 44% chance of surviving more than 3 years and 56% chance of surviving less than 3 years, right? So basically, these two numbers are the conditional probabilities here. Okay. So another cool property of the conditional probability is that if we add these two numbers, right, so 0.99 plus 0.1, I'm going to get 1, right? So the problem actually changes when we calculate conditional probabilities, right? Up here, if I add these four numbers, I'm going to get 1, right? So the summation of these four numbers is going to be 1. So if I calculate the sigma of these four numbers, I'm going to get 1. But when I calculate the conditional probabilities, the summation of each column is 1, right? So the summation of this column is 1. The summation of this column is also 1, right? This column also, the summation is 1, right? So that means that, when you're calculating the conditional probability, right, you are either in this column or you're in this column. You can't be in both columns, right? That's the meaning of the conditional probability, right? Meaning that, if you're conditioning on the type of surgery, the type of surgery is either brain cancer surgery or knee ACL. You can't be in both of them, right? And that's the reason that these numbers add up to 1, and these numbers also add up to 1, right? So in other words, f of x and y, right? The double integral of this thing is 1, right? If I look at the joint distribution, the double integral is 1. But if I look at the marginal, for example, f of y given x, then this single integral is 1, right? Similar for the other one. So once I have, once I have the conditional probability, it's only a function, it's the integral over y is 1, right? I don't care about x anymore because I have conditioned it on x, right? So x is constant. So everybody agrees with these equations. There's one more that I didn't write. Maybe I can write that one also. So integral of f of x given y, d of x, this is also 1, right? Any questions? Okay. So now I'm going to ask you a very, very hard question. So if you can answer this question, it means that you're a genius, in my opinion. Because first time I was teaching this course, in the middle of the, so this is a cool story. In the middle of the lecture, I got very confused, right? And I had to think in the class, and I think I don't remember very well, but I think I couldn't answer it, Maybe I was under pressure also. But I answered it, when I was, after the class ended, I was walking to my office. I was like, oh, now I know what's going on, right? So let me tell you what this question is. So let's go back here, right? Let me see where we have it. Like somewhere that's relatively clean. Maybe it's here is the cleanest, right? So right here, oops. So right here, I calculated, since I added some notes here, I will write it again. So f of y given x, which is a function of y, we just calculated it, right? It's 0.002 e to the 0.002x minus 0.002y, right? This is the conditional probability of y given x, right? And, the total probability must be 1, right? That means that the integral of this thing, f of y given x, d of y, this integral must be 1, right? Or we made a mistake somewhere, right? Remember that this is a single integral, right? Because it's a conditional probability, right? So our argument is y. But how is this possible, given that here I have x?
It's a constant.
Yeah, x is a constant, right? You're right. That's a very good answer. And in fact, I think in class that was also my answer. But you're right. X is a constant. That's a very good answer, right? So x is a value because we have conditioned it on x, right? But I calculate this integral. And here I have x, so at the end I will get, like something that has an x, right? I agree with you, x is a constant, but, still it has an x, it's not 1. Yeah? Yeah, you're right. So that's a similar answer. So, and in fact, that was also my answer, I think, during the class. So x is a number. You're right. So x is, for example, 0, or x is 1, or x is 2, right? And the idea is that whatever x is, right, if you plug in x, for any number of x, the answer will be 1, right? That's the idea, right? So we're saying x is a constant. Whatever the value of x is, you will get a 1, right? But that means that, how is it possible that, I have an x here, and if I plug in x equal to any number, I will get a 1. So that means that it's not really a function of x anymore, right? Like, what type of function do I have where I plug in x always gives me a constant number? That's a bit confusing, right?
Is it because the integral?
Okay, what because of the integral?
Because it's like definite integral, so when it's constant, it's in the both sides, up for the minus and after the minus, so they cancel each other.
Yeah, they cancel each other, but how? So x actually does, so if you do the integral, x cancels each other out, right? So the idea is that you're right, I mean, I am right. This is a function of x, right? And I'm doing the integral with respect to y. But you know what is the additional thing is that the range for y is from x to infinity, right? So I have an x here, in fact, right? So the range of my y is from x to infinity because this integral was actually defined in this area only, right? It wasn't defined everywhere, right? So the bounds of my integral are from x to infinity. And once you plug in the bound, the x's cancel out, right? So if you actually do this integral, right, do this function for these bounds from x to infinity, the x's cancel out, and you will get a 1 at the end, right? So, I mean, both of you guys, you were right. You know, x is a constant. So for every x, we will get 1. Any questions? Okay. All right. So again, you know, like when we have a joint PDF, we can have expected value of x. When we also have a conditional PDF, we can have expected value of x and y, right? So the conditional mean of y given x is denoted as expected value of y given x. And the equation is exactly the same as before, right? The expected value of anything is that thing times the PDF, right? So in fact, this is not a new equation, right? So the expected value of, you know, anything is that thing times the probability of, you know, y, right? So if assuming that this thing is a function of y, right? So this thing is like h of y. Right? So this is really not a new equation, right? So to calculate expected value of y given x, we have to multiply y by the conditional probability of y given x. And similarly, we have the conditional variance of y given x, right? So this is the definition, the first equation. And the second equation, you know, it's very easy to prove that this equality is correct. The second one is usually easier to compute, right? So if you want to compute the variance, the conditional variance, this one is usually easier to compute. Any questions? Okay. So hopefully it will look, you know, more clear with an example. So again, here we have the example of, you know, the number of bars and the loading time or the response time, right? So as I said before, you know, these 12 numbers give us everything, right? We can calculate everything from these 12 numbers, you know. We can calculate E of x, we can calculate E of y, we can calculate variance of x, you know, we can calculate variance of x given y. We can calculate anything from these 12 numbers, right? So the question wants the conditional mean of y given x is 1, right? So once the question says, oh, given x is 1, we know that we have to calculate this equation, right? So f of y given x, and by definition, that's f of x and y divided by f of x, right? So the first thing we have to do is to calculate this marginal of x, right? So it's easy to calculate the marginal of x. For example, here, I have to add up these 4 numbers, right? So I have to add up these 4 numbers, and the answer is 0.2. Right? And similarly, I have to add up these 4 numbers to get 0.25, and the last one is 0.55, right? So note that the summation of these 3 numbers is 1. right? And it must be 1. It always must be 1. So this is only a PDF of x, right? So here we don't have y anymore. So any questions so far? So we calculated this part. Right. So now basically we can actually write this thing here, right? So maybe we can write this in the second, in the next row. So we can say, oh, f of y given x, right? So we can extend this table, right? So or actually, I think I have to write it here, right? Yeah, okay. So I want to calculate f of, for example, y equal to 1, given that x is equal to 1, for example, right? Yeah, okay. So maybe I can correct this thing that I wrote here, because there's no space. I can't really write here, but there's room here, so I can write here. So this row is going to be f of y equal to 1. And then the next one is going to be f of y equal to 2 given x. Right? So f of y equal to 1 given x is going to be this number, 0.01 divided by 0.2. So that's 5 times that, so that's 0.05, right? And given f of y equal to 2 given x is going to be this number, 0.02 divided by 0.2, and that's 0.1, right? So basically, I'm using this equation. I'm dividing the joint by the marginal, right? Now the next one, f of y equal to 3 given x. So for that, I have to divide this by 0.2. It's the same answer, 0.1. And then f of y given, f of y equal to 4 given x. So that is 0.15 divided by 0.2. So that's 5 times that. I think 0.75. Can somebody please check the last one? So yeah, actually it is, yeah, it's correct, because these numbers, it is correct what I wrote here, because these 4 numbers add up to 1, right? So it's correct. So what I wrote here, right, in this first column was f of y given x, but my x here was 1, right? So I can continue and fill out these guys as well, right? And these guys as well. But the question says given x equal to 1, right? So I don't care about the other guys that I ticked, right? I only want the first column, this column. So basically these 4 numbers around the yellow box, they give me f of y given x. So f of y given x equal to 1, right? So I plugged in, so this is for x equal to 1, right? So any questions so far? I haven't calculated the mean yet. I just calculated the conditional PDF so far. Any questions so far about how I calculated the conditional PDF of f of, so these 4 numbers actually tell me f of y given x is 1, right? So if the question wanted f of y given x equal to 2, then you had to compute this column, right? So this is f of y given x is equal to 2. Any questions so far? So now I have to calculate the mean, right? Mean is the expected value, right? Remember, so always when the question is asking mean, you can think of the rolling the die example, right? So when we want to calculate what is the expected value of the number that we get when we roll a die, we say it's 1 times 1 divided by 6 plus 2 times 1 divided by 6 plus 3 times 1 divided by 6, right? So basically what we do is to calculate E of x, I say that's equal to sigma x f of x, right? So if I want to calculate the mean of this thing, I have to multiply these guys. So the mean, so f of, what should I write? So here, f of, sorry, E of expected value of y given x is 1 is going to be, I'm using this equation, right? Is going to be this number times y equal to 1. So 1 times 0.05 plus this number times y equal to 2. 2 times 0.1 plus now this guy. 3 times 0.1 plus 4 times 0.75, right? And at the end, I get a number, right? This is a number. So that's my final answer. Can somebody please punch this in? I'm curious. What is it? 3.55 or 2.55? Oh, then I made a mistake. Yeah, it can be actually 3 point. Yeah, sorry. So because y varies between 1 and 4, right? So the mean value can be 3 point, something. So this number is 3.55. Thank you. 55, right? So it means that the mean is around here, right? So we can check the numbers. Yeah, I think that's correct because look, the most probability is here, right? Because these guys are quite small. This is only 1%, 2%, 2%. This is 15%, right? So most of the mass is around 4, right? And because of that, the final answer that we get is also relatively close to 4, right? So I think that's correct. Any questions? Okay. So, curious to see. Yeah. So no mistake. 3.55. Any questions? Okay. And to calculate, so this question doesn't need the variance, right? It just wants the mean. But let's say we also wanted to calculate the variance, right? So the procedure is quite similar, right? So to calculate the mean, we calculated y times f of y given x. To calculate the variance, we also have to calculate y squared times f of y given x, right? So for example, 1 times this is this, right, 0.05, and then 2 squared is 4 times this is 0.4, right? 3 squared, that's 9 times 0.1 is 0.9, and 4 squared times 0.75, that's, the 4 squared is 16, so that's 12, right? And then what we do is we add up these 4 numbers and we get 13, right? And the variance, the equation of the variance is sigma x squared f of x minus expected value of x to the power 2, right? So this sigma was 13.35, and the variance, the expected value we just calculated was 3.55, right? So if you do this, then you get 0.74. Right? And again, it's positive, right? It can never be negative. Any questions? So again, you might find these, very, confusing. But if you practice a few times, this is much, much easier than chapter 2 material. If here you have to practice, 4 or 5 times. But for chapter 2, and chapter 3, to find out which equation, binomial or, negative binomial, or those are much more tricky. You have to actually practice a lot to get the hang of those. So I think these are much easier. The steps are much more, but, they are like very well-defined steps. Any questions?
Sir, can we use base there with conditional probability?
So this is, so sometimes, remember with the base theorem, we have, P of A given B, we wanted to get, so we can totally use that actually here with the, with continuous random variables as well. But we don't teach that.
How about independence?
Yeah. So, if you have time, we talk about it today. I think that's the next slide. No? Okay. So now, we just calculated conditional mean, right? So this was the conditional mean, right? And this was the conditional variance. But we calculated it for discrete random variables, right? Now we want to calculate it for a continuous random variable, right? So for the same example, for the same running example, we want to calculate conditional mean for y, given that x is 1500, right? So remember that, thing that we drew, right? So I know that my x is 1500, right? So it means that I'm somewhere here, right? And I want to find out what is the average value of y, right? So the average value will be like something here, right? I want to find out what is this. This is expected value of y given x is 1500, right? I want to find this value. So what I do is the first step is I have to find f of y given x is 1500, right? That's the first thing I have to do. If I want to find the conditional mean, first I have to find the PDF. And remember to calculate this. I emphasize this. We have to do f of x and y divided by f of x, right? So first we have to calculate the marginal distribution of x, right? So we did all of these before, so I'm not going to repeat those. The final answer that we got was, was this. Right? So sorry, not the y part. So this part, right? So this is f of y given x is 1500, right? And now I'm multiplying y by it because I want to calculate the expected value. Okay. So, you asked what is the hardest integral we have to do in this course. In my opinion, this is the hardest integral we have to do. So it's integral of y times, so this is a constant, right? This comes out, but e to the something, right? So integral of y, e to the ay, d of y, right? Does anybody know what's this integral? Yeah, exactly. We have to do integration by parts, right? So I think this is the hardest integral you have to do for this course, right? How I like to do instead of integration by part is the following, I say, oh, so this integral is going to be y e to the, so instead I try to find the function whose derivative is that guy, right? So e to the y, right? So now, so the first term that I need is this term, right? Because the derivative of this is going to be derivative of this times derivative of this plus derivative of this times derivative of, So if I have f of x times g of x, right? The derivative of this is going to be f prime g plus f g prime, right? So the derivative of what I wrote here is going to be first derivative of y times the other function, so 1 divided by a times e to the ay plus derivative of the exponential times this. So derivative of exponential is exponential, but a and a cancel out. So it's going to be y e to the ay, right? So I just wrote the derivative of that down here. This is what I need, right? So this is my function, but this is what I don't need. I need to get rid of this, right? So now I'm going to write the integral of that thing. So that is plus 1 over a squared e to the ay. Yeah. So I think this is the hardest integral that you need for this course, right? So, I don't want this course to be, on integrals, and I don't want you to worry about, integration by parts. So if the crib sheet doesn't have this equation, I will add it to the crib sheet so that you don't have to worry about, I don't think, you should worry about, remembering this or trying to do integration by part for this course. It's not really, the focus of this course. So I will, does anybody know if the crib sheet has this equation or not? Yeah, if it doesn't, I will add it, to the crib sheet so that for both sections, for all 3 sections, so you can use it for the exam. Is this actually? I think it's correct what I wrote. Can somebody check? So is the derivative? I think what I wrote is correct. The derivative of this thing is actually this function here. So the rest of this example is just using this equation and plugging in, right? I will do that. It's the end of the class, so I will use the 5 minutes remaining to give you the midterm. So I will use this equation in the next class to solve the expected value of y given x, and then I think the next concept, which is a very interesting concept, is the concept of independent random variables, right? So this is really, really cool, and I encourage you to come to the class on Monday because it's quite interesting, when you talk about independent random variables for, continuous random variables like x and y. It's very cool.